This is a sensor that really only does one thing: sensing pressure. It is really small. Look at in between these copper plates right here. There's a little strip in the middle. Might be a little bit hard to see, but it's black. That is the main sensing bit. To see how big it is, screw it for scale. It is pretty small. I've been researching pressure sensors online, and there has been a pretty consistent problem. Look at all of these listings. All the sensors available are pretty huge, and they're bulky, expensive, and honestly a bit outdated for modern applications. The ones that are pretty small already are sometimes even bigger than my thumb, and for precise surgical applications, that's not gonna work. So I'm making a really small one myself. I'm Ian, and let's get this started. You might be wondering why I said the word surgical applications before, and that why I'm pretty obsessed with making a tiny little sensor. And that's because I'm working on a project with surgical robotic arms. Current surgical robots have a pretty interesting problem. They can't really exactly feel on what they're touching. Let me demonstrate why this matters. Imagine the difference between these two scenarios. When I pinch at full strength, it definitely hurts. But a gentle pinch is totally different. Both are pinching actions, but the force makes all the difference. In surgery, this kind of sensitivity is crucial. You'll never know if it is just enough to grasp the outer surface of an organ or any particular place inside your body, or you're grasping it too hard, accidentally ripping apart a scar from a previous surgery. In that case, you might have to go for an open procedure, whereas the doctors have to go straight in on themselves and not using the robot, which kind of ruins the purpose. Therefore, to add the sense of feeling, there has to be a pressure sensor to fit on the robot's tip while maintaining sensitivity. Now, I'll be honest. I've never built a pressure sensor before. Actually, I haven't built any sensors before. I've used them for certain kinds of projects like IoT devices or robotics, things like that. But building one from scratch is completely new territory for me. And so therefore, it is necessary for me to get to know how sensors work in the first place, and explicitly pressure sensors. Well, Google gives a pretty good answer. It detects a force and converts that into an output signal that is relative to the strength of the pressure being exerted. But these are pretty standardized answers. Going down this path might just bring me down another rabbit hole of those bigger, bulkier sensor designs, and that is not what I'm looking for. So I might have to look for a different way. This is where graphene comes in. And it's pretty amazing stuff. Picture a single layer of carbon atoms arranged in a perfect honeycomb pattern. What makes it perfect for our sensor is not just its size, it's how it reacts to pressure. When you press on graphene, its electrical properties change in a very predictable way. Plus, it's biocompatible, which is crucial for medical applications. Through my research, I found this fascinating paper about using laser-cut polyimide films to create graphene. The beauty of this method is that it solves two problems at once. We get our graphene layer, and we get a stable base to put it on. I chose to use a 2mm thick film, matching what worked in the research. Let me break down our design. Since this is a prototype, we're probably going to keep it simple, but it has to do what it needs to do. A strip of graphene in the middle, protective layers on top and bottom, and contact points for measuring resistance. And here is a pretty good stroke of luck. My high school actually has this exact laser cutter that I need, which is the laser cutter that the researcher used in the paper. When I mentioned this project to my advisor, she showed me this machine, and it is perfect for what we're trying to do. There also happens to be polyimide film tape on the internet, and this is just a prototype. Using tape as initial protection mechanism seems okay to me. Whereas the contact point now is a little bit tricky. I need to have something that conducts electricity that allows electricity to flow through the sensor itself without damaging it when I bring the sensor around and things like that. So I asked AI. He gave me a selection of methods, out of which I chose to use copper plating along with silver paste, as it seems the easiest to do. So here's everything that we need. We got our polyimide film, our polyimide tape, our silver paste is a bit difficult to see, but it's right here, and our copper plating. And of course a pair of scissors to do the cutting. With the laser cutter to our left, let's get this thing built. Look at this piece right here. Look at how small it is. It's so small. Like, let me show you this real quick. So, compared in scale, it's not that bad. It can be even smaller, so yeah, this is exactly what we need for our application. Now I'm going to apply our copper platings, our polyamide tape, our silver paste, with this piece of graphene that we have right here. I'm gonna cut out a small piece, one piece out of the 3 that we have, because you know, sometimes things get faulty, and so I wanna pick the one that looks the best in appearance, which is, look right here. The 3rd one has a bit of a crack in the middle, as you can see. It's sort of visible, and I think it might affect its performance. So I'm going to cut that piece away. I'm going to use one of the 2 remaining pieces. Yeah, let's see what we get in the end. This is completely optional, but you can have something like a piece of glass on the bottom. When you cut out this thing, you have a bit of a thing under it to keep it sort of clean. After 1 day of leaving it alone, here it is. I remove 1 layer of tape on top because after it dries out, you can just sort of take it off. I'm just doing it to prevent the copper platings from accidentally nudged by some other students at my school. And so yeah, here it is. This is our full sensor. It may be small, but it is full of potential. I also got a digital multimeter with crocodile clamps and wires to see how good our prototype is. You see, if I press on top of the sensor, the voltage value goes up, and which means that the resistance value also have gone up according to V equals IR as the current value stays constant. The reason I'm not using resistance directly is because it might have been too much for the digital multimeter to handle because it says overload when I click on top of it. That's why I used voltage. And as you can see, it sort of works now. If the harder I put my hand onto it, the higher the voltage value goes. That means that this can also work onto surgical robotic applications. The harder I pinch onto something, the higher the voltage value would be. This is exactly the kind of sensitivity we need for surgical applications. The next phase of this project is to integrate our existing sensor onto surgical robotic arms. What we need to do is that we need to develop signal processing, create a software that does that, and does that in real time. I also need to have proper housing for the sensors and the contact pads to make sure that it doesn't break when we do anything with it. But that will be a story for another video. See you all next time.